I'm going to introduce our speaker now. Professor Natarajan has been at Yale for some time now. That's her primary job as a professor in the Department of Astronomy and a professor in the Department of Physics. But she has all kinds of other responsibilities and things she's done, and you are encouraged to go and look at the website that I imagine she's had something to do with constructing. But I wanted to take us back just for a moment to her earlier career. She did her first degrees at MIT, and then she did the sensible thing and went to Cambridge to do her PhD. And she got a research fellowship at Trinity College, Cambridge, which you may have heard of because I'm there too. So here we have another from Trinity College, Cambridge, with a PhD from Cambridge. In her case, I suppose Martin Rees was probably her supervisor, who is certainly one of the most exciting and interesting of cosmologists around. But here's another. I was intrigued by some other things that I read on the site. I have to tell you the title of a conference that she organized, which I took a note of. Why is there anything in the universe? And of course it occurred to me straight away we must be there to feed black holes. And that seems to be the subject that she's now adopted for this evening's talk. Fasting and feasting, the feeding habits of black holes. And you'll get some film. I know there's a film later on tonight for those of you who go to the TV room, but you're going to get some films now, provided it's all working.
Thank you so much, Jim, for that very kind introduction. Okay, so I've had two very strong intellectual interests over the years, and have worked on two problems. So one of them is trying to understand the distribution of dark matter in the universe, and that is done by looking at light, at the way light propagates through the universe. And the other problem that I worked, in fact, this is a problem that I worked on for my PhD thesis. In Cambridge, you don't actually work on one problem for your thesis if you do a theory PhD. You work on a bunch of different problems, you learn a lot of different techniques and tools, and you learn to think differently. But the problem that I started working on then, which I've sustained interest in, is understanding the growth history of black holes in the universe. And what do we mean by that? So the fancy way of saying growth history is, the fancy term is called accretion history. So it's understanding how the first black holes in the universe ever formed, how they grew, and how they evolved over cosmic time to produce the black holes that we actually see today. So what I want to do tonight is to try and give you a flavor for what the current status of the field is in terms of black holes. So the first thing I want to tell you, if you're wondering, and you might have heard about black holes mostly from sort of science fiction, they are real, and there's one in our neighborhood, okay? So they have been discovered, and you find them everywhere in the cosmos. In fact, it appears that pretty much every galaxy in the universe harbors one in its center, including our own galaxy, the Milky Way. And it turns out, as I said, that when you try to understand the growth history of black holes, that they go through these phases of growing and not growing. So they're either feasting, they're feasting on gas. So black holes grow when gas accumulates around them, and then it gets sucked in and fed into the black hole due to the black hole's gravity. And they are sometimes starved of fuel. They are starved of fuel when they have absorbed all the gas that's around them, all the gas has been gobbled, and there's nothing left over. So black holes like that get choked, and they're fasting. So luckily for us, the black hole at the center of the Milky Way is currently fasting. By the way, the black hole in the center of our galaxy is so far away, and it is not very massive. It's only 10 million times the mass of the sun. It's about 1 million times the mass of the sun. It's not very big by cosmic standards, as I'll show you in just a minute. So we don't have to worry. So I just want to assure you all to have your dinner, so you're not going to be worried now about some black hole that's going to gobble all of us up. Okay, so you must have all heard of these rather exotic objects. So what black holes really are a mathematical solution to how space reacts when you have mass in space. So Einstein's theory of general relativity tells us, explains to us, that space and time in the universe are bound together. And they are bound together, and the way you think about it is that you think of this entity called space-time, which has 4 dimensions. So you have 3 of space and 1 of time. And the reason you kind of bind them up this way is because when an event occurs in the universe, wherever it occurs, in order to know where it occurred, you actually have to specify when it occurred. The reason for that is, even though the speed of light is quite fast, it's 186,000 miles per hour, you find that it takes a finite amount of time for light signals to reach us. So if I look out in the universe, right, so when we look at the sun, right, it takes light 8 minutes to reach us from the sun. The sun is our nearest star. So if something happens to the sun, if it shuts off, if the nuclear energy that's being produced by the sun shuts off, we won't know for 8 minutes, right? And remember, that's the nearest star, because that's the time that it takes for light to reach us from the sun. And when we look at more distant objects, it takes longer and longer for light to reach us. So when we look out at the night sky and you see these very faint, distant galaxies, it's often taken billions of years for light to reach us from those galaxies. And that's pretty astounding, which means when you're looking out into the universe, you're looking back in time. So you're looking at this galaxy as it was 1 billion years ago. We have no idea what it looks like today, and we never will. Okay? So this is sort of one of the sort of basic sort of facts about the universe. So one other feature of the space-time, aside from the fact that the entire universe, we all live on space-time. There's nothing above us, there's nothing above space-time, there's nothing below space-time. Everybody, the entire universe, exists on space-time. We are confined to this. So mathematically, it's called a manifold, for those of you who are doing abstract mathematics. So the presence of mass, so you can think of space-time as a fabric, as a sheet. So the presence of mass curves space-time. So what I'm showing you here is a visualization of space-time, the fabric, with those metric lines drawn, and the presence of a mass. In this one, sort of a gentle introduction to black holes. This is not quite a black hole, because this is not quite what the black hole does. So if I drop some mass onto space-time, it causes this little bump, this curvature, or this pothole, if you will. And the more massive an object, the deeper the bump. Okay, so the deeper the pothole that you create. So it turns out, so the presence of mass tells space-time how to curve, and space tells mass how to move. Okay, so this is sort of, they're very profoundly connected. And yet one of the reasons most of us physicists really adore Einstein is not because of his hairstyle, right? It's because he came up with this extremely profound insight that the geometry, the contents, and the fate of the universe are intricately tied. So if you know two of these three quantities, you can determine the third one. And that's because he had the audacity to actually model the entire universe and write out an equation for the evolution of the entire universe. Before him, no one imagined that you could actually write a DDT, a rate of change of the size scale of the universe. So that's why his contributions are fundamental in terms of understanding anything about the cosmos, including black holes. So what is a black hole really? So remember, you just saw this graphic. In fact, a black hole is so densely packed, right? The density of how densely packed the mass is so extreme that it actually causes a puncture in space-time. So it's like an infinite puncture. So you see that here. So you see that visualized here. So in fact, what a black hole does, it causes space-time to curve infinitely. I can't draw infinity. No one can draw infinity. So what you really see here is sort of give you an idea of what the black hole does compared to what the sun does, or a white dwarf, which is a denser star than the sun, and a neutron star, which is even denser than a white dwarf star. So matter is packed much more tightly. And notice, as the density goes up, notice what it's doing very peculiar things to space-time. So the interesting thing about a black hole is the kind of pothole that it creates in space-time is such, it is so deep that even light cannot escape. So once it crosses this magic ring on the top, which is called the event horizon, which is a size scale for the black hole, even light cannot escape and come back out. Okay, I'll tell you at the end what would really happen if I fell into a black hole, or one of us fell into a black hole. So the question is, okay, which is great, this sounds like a good mathematical theory, so how real are they? So let me just show you. First of all, in the upper panel is an artist's impression of what a black hole really looks like. So this black object is a black hole, and what you're seeing here are gas flows. So you're seeing color-coded gas that is flowing in. So some portion of the gas, the gravitational pull of the black hole is pulling the gas in, and a small fraction of the rest mass energy of the gas, because energy, remember, E equals mc squared, so a small portion of the mass gets converted into energy of the gas, and it starts glowing in the X-rays. So it's being pulled apart, it's being heated, and you can see the gas going in. Of course, as I just finished telling you, once it reaches this event horizon, the magic distance beyond which it's a point of no return, that's it. The mass is gone, it gets eaten in by the black hole, and it adds to the mass of the black hole. Okay? And so this is the artist's impression, and as this process this is what is called accretion, this is how black holes grow, this is how they feed, so this is an actively feeding black hole. And how do you know when a black hole is actively feeding? As I said, it glows, it glows in the X-rays, and sometimes it can glow in visible light as well. And often you produce these jets, very, very bright jets that you see in the universe. So let me now show you in the real universe. So this is, quasars are actually powered. These are very, very bright objects that are powered by accreting black holes. So they're very luminous, and they're very luminous because of the rest mass energy of the gas that's feeding them, that portion of it, a small portion of it, that gets converted into some kind of electromagnetic radiation, some kind of light, either X-rays or visible. So this is an image of one of the quasars that is nearest to us, and it's called 3C273. And notice, this is a Hubble Space Telescope image of it. It is so bright that it saturates the camera. Okay, that it's very nearby, and it is so bright that it completely saturates the camera. And those of you who've tried taking a picture of a very bright lamp with your iPhones, you know this happens, right? If you saturate the detector, your camera, these are the sort of spikes that you get. You get these diffraction spikes. And So that is looking in the optical, and then you can say, let me try and trick and put a different filter, look at it in a different wavelength. And when you look at it in a different wavelength, when you look at it in the infrared, you see something quite different. What you see is you start seeing all the gas that is very hot. The hottest gas glows, and the colder gas, you don't actually quite see it in the image anymore. So notice, look at the artist's impression. So remember I told you as the gas is going in, it's heated up to very, very high temperatures. And we're talking about 10 to the 7 Kelvin, 10 to the 8 Kelvin. Extremely hot. And so that's what you end up seeing. So not only are black holes that are feeding, these accreting black holes, they're not really theoretical objects, you actually see them in the universe. And these are the nearby ones. Because they're so bright, you actually see them out to very, very large distances. So quasars are the real beacons of the universe. You can actually see them out to the largest distances. As I mentioned just before I started, that unfortunately, not every black hole is actively feeding and is fortunate enough to be fed. So there are lots of black holes that are left hungry and they're fasting. And one of them is the black hole in the center of the Milky Way. So what I'm going to show you is incredible data. This is real data. And what you are seeing marked with the star is the location of the black hole in the center of the Milky Way galaxy, our galaxy. And what you see as these bright objects, color-coded, are individual stars that are orbiting that black hole. So because of the gravity of the black hole, these stars are unbound objects. And all of you who've studied Kepler's laws know that these orbits have to be ellipses, right? And now, because this black hole is not so massive, the orbital time that it takes for these stars is about 10 years for several of them. So this is incredible data from 1995. You'll see the clock there. And one of my colleagues and good friend, Andrea Ghez, she works at UCLA, and this is from her group. So let me show you, I want to show you the spectacular movie of the real orbits. This is data, okay, and you see the time. Notice several of them close. It's incredible. I mean, this is proof of Kepler's laws as well. And the other thing that it allows you to do, it allows you, for those of you who've studied a little bit of physics, that once you have one closed elliptical orbit, you can calculate the mass, the gravitating mass in the center. So this is the way in which we've computed the mass of the black hole at the center of our galaxy. It's one of the most accurate mass determinations, other than the mass of the hydrogen atom, that we can determine in the lab really well. It's quite incredible. I'm always totally bowled over when I see this movie, and I can show it to you one more time if you want. It's available online, and you can go download it, and you can see it. You can see it from visualized in a bunch of different ways. This is the simplest visualization where you're just shown with the real data, the velocities, and you track and you see the orbits of these stars. So now the technology that we have, so the center of our galaxy is a very dusty place. There's a lot of dust, and you can't actually see through with visible light. You have to see it through infrared light, which will penetrate the dust. And so this is an infrared image, so infrared tracking. Notice then the center of our galaxy is also a very crowded place, as I'll show you. And so the ability of our ability to resolve these individual stars is just really immense. This was not possible before 1998. So this is really state of the art in the field. And those of you who sort of are reading all the time, you must be wondering why suddenly all these newspapers and magazines are talking about astronomy all the time. It really is the golden age of astronomy and cosmology. So since about 1995, there have been major technological developments that have enabled incredible kinds of data to be collected. So this is one of them. What I now want to show you, you may say, okay, this is great, but how did the black hole come to be in the first place, right? So this is a simulation that one of my students did for his PhD thesis work at Yale. let's see if the movie, yeah. What you're seeing here are a simulation. So what you're seeing is a piece of the universe, piece of the very early universe, about 500,000 years after the Big Bang, okay? And what you just saw were gas flows in the very, very early universe. And you're seeing these yellow streams is hydrogen, mostly hydrogen gas, and the color coding is density. So the innermost region that's very, very high density is shown in red. So this region that we've zoomed in on is actually a potential site where the first black hole is going to form. So that's the problem that I've been working on now for about 7-8 years, trying to understand the physics of what physical processes are important in assembling the first black hole. Remember, I told you that black holes are so dense, they're denser than any other matter that we know. And the question is, how do we pack, what physics do we need to have happen so that we can pack this kind of matter down? And so we're on our way. We don't quite, I can't show you a movie yet of the black hole that forms because we're not quite there yet with computation. We can't follow it. Once it gets this dense, as color-coded by the dark red in the center, we just don't have computers that have the speed to follow the evolution. The rate of change and the flow of the gas is just so rapid that we don't have the technology yet. But it's improving every year. We can look further in. We can see it packed a little bit more. So I would say watch this space. In 5 years' time, we may have something quite incredible. Meanwhile, let me try to give you a sense of where black holes really are in terms of the larger scale of the galaxy. I just zoomed in on our galaxy and I showed you. So this is another galaxy, a nearby galaxy. And what we're going to see is, just to give you a sense of spatial location of where the black hole sits, we're going to zoom into, this is real data from the Hubble Space Telescope, we're going to zoom in up to a point that the data will allow us to, and after that you'll have an artist's impression. As I told you, right, we don't know exactly how to pack the black hole and make the black hole, but what we do know is by the time a black hole grows, it's formed, and it grows enough to sit in the center of a galaxy that has these many stars around it, we then know what the structure of the gas has to be. So what we're going to see now in this movie is a zoom in of real data as far as the real data can take us. So, we can keep zooming in just as you zoom in when you make a movie or something. And then finally, we reach the final stage. So this is the black hole. This is the feeding disk of the black hole. This is the gas disk that's going to be feeding it. And remember, this last bit, as I told you, is an animation because we haven't solved that problem yet. But this is how things connect up. So every galaxy in the center, right around the center, has a lot of stars and then has a black hole that's seated in the center. And then it has this big red gas disk that you see, which is the feeding disk. And you can imagine one of the things that is missing in the Milky Way, in the center of our galaxy, is a feeding disk. We've exhausted our disk. There's no gas left. And that's why our local black hole is fasting, right? The majority of black holes in the universe, our nearby universe, are actually fasting. And most of the black holes in the early universe, which was very gas-rich, are actually feasting. If you think for a moment, you'll see right away, why is that? So imagine, why are we losing gas as time goes on in the universe? Because stars are forming. Stars form from the same gas. So stars also form from gas, from cooling gas, and black holes are fed by gas. So what we've been working on, me and my group, is work that I started with one of my postdocs in 2005 and 2006, is a completely new way to make, remember I was telling you the challenge is how do we pack and make the first black hole. So what we have is a completely new way to make very, very massive seed black holes, to make the oomphiest objects quite early on in the universe. So I'll just give you an outline because this is sort of the state of the art. And now there are many, many groups around the world that are working on trying to test our model, do better calculations, look for data, look for signatures. And I'm happy to say that the evidence is growing and gathering in support of this model. But as you probably all know in science, right? I mean, it really doesn't matter. The thrill and the excitement is that you're able to make a prediction, and I'm excited whether it gets proven right or wrong. It doesn't matter. I mean, the fact that you can make a prediction that people can go out and observe is just really exciting. And what is very exciting about doing science and cosmology now is that, when Einstein wrote his papers, right? He wrote a paper in 1905, and it took 1919 to 1924 to verify his result, okay? Now, we wrote this paper in 2005, 2006. By 2009, we already had evidence supporting this model. So this is what is exciting about doing science now, especially cosmology. You don't have to wait for a lifetime for verification. You don't have to wait for 10 years. The amount of empirical data that we have streaming in is just enormous. So models and theories can be ruled in or ruled out very, very rapidly, which is super exciting. So this model that we came up with, I'll just give you a brief, it's quite technical, but the principle is very, very simple. And the idea is that you make, in the very, very early universe, very massive disks to start with. So you have you have these sort of dark matter halos, which are the places where galaxies form in the universe. And you have a lot of gas, hydrogen primarily, that forms a very massive disk. This disk becomes unstable. There are instabilities in the disk. It goes unstable, it fragments, and it forms a very dense black hole in the center. So what is nice about this model is that we are able to link the physics of the large-scale environment to the small-scale black hole that forms. We're able to couple these scales. And coupling these scales gives you intuition. You can actually analytically calculate without computers up to a point. And as I said, then, in fact, it's the very fact that you've coupled these two very different scales that makes it very challenging. But that looks like it's the right kind of challenge for describing what most likely happens in the universe, the coupling of scales. So this is hot off the press. We are running these computations at one of the largest supercomputing facilities. It's the second fastest computer in the world that is in the United States, which is at a computing center in Illinois, in Urbana-Champaign. So this is a movie that one of my students just sent to me before I came on my trip to Hong Kong. So what I want to show you is that now, remember we saw that red blob in the center of the gas flows? Now we're zooming into it by a factor of 64 each time I zoom in. So it's 64 times 64 times 64. So you see 64 to the power 5 are zooming in. And we still don't see the black hole, but you can see that, again, the color coding now is that the purpler it is, the denser it is, that we are seeing further and further into the densest core of where the seed black hole can form. And remember I told you it's a challenge of scales, right? How deep in we can look. And we're getting pretty close. This is pretty amazing what we have here. And at this point, we just need, so this process of zooming in is called refinement. So those of you who are computer scientists might have heard of adaptive mesh refinement, and that's the technique that we are doing here. And we have refined now by a factor of 512 cube. I mean, that's really stupendous. And what that amounts to is being able to see from New York City, say, I'm sorry, all my analogies are about America. I just went to Victoria Park today, so it would take me a little bit of time to compute. So if this is like resolving the hair, one hair on the head of a person who's standing on top of Empire State Building from the edge of Battery Park City. For those of you in New York City, it's the tip. It's the southernmost tip of Manhattan. So that's that's what we're capable of right now. It's tremendous. I mean, we're not done yet. Okay, we're far from done. But that's the kind of physics, the precision with which we can probe physics now in the early universe. So what we're seeing here is sort of the core region. You know, I don't know how well the movies are actually showing. I hope you can see the inner region there. So now the color coding has moved to sort of mustard, to yellow, to mustard. And those are sort of the densest regions. So what we can do, as you can see, right, so the kind of work that I do and a lot of people who work on black holes do is called phenomenology. So basically you see the phenomenon, so you have data now, and you have a theory, and you connect them. And as I said, you can either rule in a theory or a mechanism or a physical process, or you can rule it out. So where are we at the moment? So at the moment, we're working on this paper that we're hoping to submit to Science in a couple of months. When we go as far as we can in the computation, as I said, we can probably go a couple more levels. So what we find is when we zoom in on this region, and you just saw the movie, at the end state, this is where we are at. So what we find, intriguingly enough, remember in the cartoon that I showed you this nice little gas disk, and I showed you one black dot. And I said, there we form a black hole. So what we actually find, physics-wise intriguing, is that there's a lot of dynamical activity going on. That you form this very dense blob, and then this blob is dancing around, and then it splits into two, right? So it looks, so in the universe, stars most naturally form in pairs, okay, in binaries. And nobody thought, we definitely did not think so, that black holes might also form in pairs. And it looks like black holes likely form in binaries, but I can't say that for sure quite yet, because these may yet merge and become one blob again, right? So as I said, watch this space. And I just want to show you, I want to give you a flavor for what it is like to do the kind of work that I do, and what is it that I sort of wake up at night thinking about. And that is sort of the calculations and sort of figuring out, making sense of what's really going on in these calculations. Ultimately, the computers are very good, they're very accurate, but we need to understand what's going on in terms of the physics. So this is the sort of work that one does. So what you're looking in on the right-hand side is a very zoomed in version. You're looking at the heart of the red zone that you see on the left-hand side. And you're looking at, as you can imagine, we have to do many, many realizations. So we have to do many, many mock galaxies in the early universe to see if the properties of the black holes that form in these various places in the universe, which have slightly different environments, how different are they? Are they the same, or how different are they? And are they different in any way other than just the mass? So it turns out there's one fundamental way in which black holes can differ. Some of them are born spinning. And they're literally like a top, they have angular momentum, they're spinning. And you can imagine, it's very complicating, right? Because I showed you this nice picture of space-time. I showed you this nice little singularity, and I told you there was a black hole. Imagine that whole thing is spinning pretty rapidly. It does very bizarre things to space-time around it. In fact, it does such bizarre things, it twists space-time so dramatically that it will twist light. So there's some very interesting signatures for spinning black holes that you see that have not yet been detected. So now I've told you quite a lot about black holes that are actually fasting. And I've told you, well, you get rid of the gas. The question is, black holes need to grow by a factor of about 1 billion within a few billion years of the age of the universe. So this is the other thing about cosmology. I have no difficulty imagining 1 billion of anything, right? So 1 billion years, well, that's a wink, right? The age of our universe is about 14 billion years. And the most massive black hole that we see around us is 10 billion times the mass of the sun. And when we make them initially, as I said, when we saw the movie, when the universe is about 500,000 years old, not even an infant, right? It's the very early instant of the age of the universe. You make these seed black holes, the kinds of models that I've been talking about, which are about 1,000,000 times to 10,000 times the mass of the sun. So you have to remember, you have to grow them by a huge factor. You have to feed them a lot. You have to force feed them. So how does the universe force feed these black holes? It turns out that in the universe, early universe is actually a very violent place. Galaxies are constantly colliding with each other. Okay? And so what you are seeing here is again a simulation of two galaxies that are gas-rich, and this is a head-on view, so it's a top view of two spiral galaxies. What you're seeing here is the gas, color-coded again in temperature. The bluer color is cooler gas, the whiter gas is hotter. And these kinds of collisions are very, very common in the universe. Why are they relevant? They're relevant because both of these galaxies already have seed black holes in them, right? So what happens to these two galaxies are going to merge. They're going to collide, they're going to merge, they're going to be one hot mess. Question is, what happens to the black holes in the center of these galaxies? And one notices, so what you see there in red is what we call a shock in astrophysics. So those of you who've studied physics probably know what these hydrodynamic shocks are. These are discontinuities in the temperature and the density of the gas. So notice that the gravity of these two colliding galaxies kind of keeps bringing them back and forth together. Notice how violent it is. You're blowing all this gas out, and in the end, you're feeding what is going to be one huge monster in the center, which is the merged binary black hole from the two galaxies. And you end up, the reason I'm showing you this portion of the movie is that you see objects at these various stages, real objects in the universe that correspond to the various stages that you just saw in the movie. So this is a movie that's produced by some colleagues at Carnegie Mellon University. Once again, notice the time scale, right? It's 1,600 million years. So that's how long it takes for these two galaxies to finish their collisions. So it is this kind of process that feeds black holes, and this is how black holes actually grow. And remember, when we just saw in the movie the final stages, maybe I should show it one more time. In the final stages of this, there is a stage when you have two black holes. I mean, they're still two separate entities. Before they merge, they grind down, and they become one black hole. So I've been doing work for a couple of years now, also in trying to understand sort of the dying gasps of these two black holes. It turns out there's something quite phenomenal that happens. Remember I told you about twisting space-time. So when space-time is twisted that dramatically, it generates waves. And these waves are called gravitational waves. They're as yet not detected. They're predicted by general relativity. And we know that whenever space-time is badly shaken up, it gets rippled, and we would see the ripples. Okay? And so the point when two black holes merge, you get this burst of gravitational radiation. So this is a prediction that has been made. Einstein made that prediction. And we've actually now calculated, and I want to show you, this is a paper that I wrote a few years ago with a couple of colleagues, which is really trying to understand the dying gasps. How does the final merger of two black holes, which was sort of the last point where we left the previous movie. This is also a simulation. But the interesting thing about these simulations, you're like, why is she showing us all these? The point is, as I said, the various stages you see in the simulation, you actually see in the real universe. You see objects exactly doing that in the real universe, okay? With those properties, with those separations, with that much gas, with this much gas spewing out, those jets, etc., etc. So now this is a very, very a fun calculation, and it turned out to be a lot more interesting than we originally thought it would be. So what you're seeing here again is, remember now the red, if you remember correctly, is the feeding disk. So now there's a disk of gas and there's a primary black hole that is marked with the dark dot there. And this is the top view of the secondary is going to come zooming in. It's going to come zooming in this movie because of the result of the merger. And you will see very quickly where it is zooming in. And it starts zooming in, and notice what it does to the rest of the disk. It sets up waves in the rest of the disk. And you can see these yellow rings, and these are going to be places where the gas is hot enough that you're going to see electromagnetic radiation. So you are going to see these flares, which we see now. And so what we predicted was how frequently you should see this flare, how periodic it should be. Remember, it's sort of periodically grinding in. So we predicted the light signal, and these signals have been detected now. So one other amazing thing that has not yet been detected that is predicted, this is the thing that I'm sort of really holding my breath for the next couple of years, is notice the inner part of the disk, right? You see it's black, so what's really happened is that you evacuated all the gas. So the black hole at the center has gas left over, and there's nothing here. You've kind of evacuated, it's empty. So it's like you've carved a nice little annulus, like a little donut. Basically, it's an empty donut of gas that you've removed. And you say, why is she so excited about an empty donut of gas? Well, I'm very excited because guess what happens? Once this guy has merged in and the gas, the inner bit of the gas that's in here gets exhausted, right? It's going to get gobbled by the black hole. Once that goes, what have you done? You have made a feasting black hole a fasting one. So it shows exactly how you go from feasting to fasting. So, so that's the prediction. So the prediction that we've made, that we're waiting now for data to see if this can be detected, is this transition. Because, you know, you have to have the full story, right? You need to form them, you need to grow them, and then you need to understand how they change. And so this is the final missing piece in the black hole sort of food supply story. And that is the transition. So how do you go on a diet? How do you put the black holes on a diet? And basically you starve them once you have a merger and the gas is evacuated from the inner regions. So, and what is shown for those of you who are doing science and generally sort of busybodying and want to know about what all these graphs are. There's a little graph in the little panel there. That is what is called the profile of the disk from the side view. So what you are seeing is the disk is getting eaten, and notice at the final stage, this is the gap. So you've cut the disk now. You've cut out the disk, you've made your little donut, you have an outer disk and you have an inner disk. And as soon as the gas in the inner disk is going to be gobbled, that's it. It's going to take a very long time for gas from the outer disk to start filtering in and filling in the hole. Okay? It'll take longer than the age of the universe to do that, which means you basically choked the gas supply. It basically means you've stunted the growth of black holes. So this is sort of where things are at the moment, things that need to be verified. And so what I want to show you is a discovery that I was involved with, in which we had a press conference when at NASA a couple of years ago. You know, and so NASA was very, very excited because this was sort of the discovery of the decade. Well, it was 2011, right? But still, early in the decade. But it was pretty astounding. And what this was, remember I said that this there's some proof for the theory that we had proposed on making the first black holes in the universe. So part of that theory, the cartoon that I showed you, predicts some correlations of the size of the black hole with the brightness of the quasar that is associated with it when it's feeding at very, very early times in the universe. So this is from a very deep image from the Hubble Space Telescope again, on a region where we managed to find a whole bunch of these baby black holes. And not only did we just find them, but we were actually able to measure their quasars, because they're actively feeding black holes. We can measure the luminosity or the brightness of the quasars, and they match the predictions that we made. So let me just show you. This is, I did not make this movie. It was made by professionals. It's absolutely beautiful. This is all real data, again. And what we are zooming in is to a patch where the deepest data ever taken in the universe is this patch. It's called the Hubble Ultra Deep Field. I mean, it's the deepest look ever in space. And that corresponds to about looking at the same patch in the sky with Hubble's cameras for 5.5 months. Okay, so of course it's collected, right? Because it's in a geosynchronous orbit, so it's moving, but it's passage 5.5 months worth of data that was taken over a much longer period, over a couple of years. So what you are seeing in that little panel with these, these early black holes, they're very bright quasars, but they're very dim because they're extremely distant. And as you all know, the brightness of objects falls off as 1/r². So the farther an object is, the dimmer it is going to be. So even if you know what its intrinsic luminosity, it's like knowing that a bulb is 60 watts, right? You buy it in Hong Kong, you buy it in Cambridge, it's 60 watts. It's the same 60 watts. And I know that if I have my nose up to the bulb, I know how bright it is. And if I move it further away, no matter where I move it, either here, Timbuktu, whatever, I know that if it is dimmer, it's dimmer because it's dimmer by 1/r² of how far away it is from me. So these objects that are standard candles, so it's 60 watts is a standard candle, right? So the universe has standard candles. And so we can actually then look at the brightness of the object and figure out how far away it is, because we know how intrinsically bright it should be. So these are some of the farthest objects. These are the most distant objects ever detected, most distant galaxies. So they're baby galaxies. There are very, very few stars have formed, and the thing that's formed first is the black hole. And what is shown in the little panels up top is gives you a sense of the significance of the result. So we've stacked, so all these little yellow circles that you see, the reason you can't quite see those baby black holes glowing is because they are really quite faint. I mean, they're there, the signal is there, but they're very, very faint. And you can't individually detect them. You can't see them individually. However, if you stack them, you put them on top of each other, then you have a very, very strong detection. It's a 6.8 sigma, for those of you who know statistics. It's extremely robust detection. And that's what is shown there. And what is shown here are the detections, 6.8 sigma and 5.2 sigma, in 2 different wavelengths. So, the thing is, could it be, we have to test to see, could these be some other objects that are mimicking black holes? And it turns out that the test is that we've predicted that if you look at black holes in 2 different wavelengths, so this is looking at 2 different visual wavelengths, and you stack them, then you actually have to see them in both if it's a black hole. If it was a supernova, for example, if it happened to be a supernova, right? So all of you know that supernovae are the end states of stars. The stars explode and they leave a supernova, and they're very, very bright. And those are standard candles, so you could confuse them and think, maybe what we're seeing is a supernova. But if this was a supernova, you would see it only significantly on stacking over there, but it would be absent from this image. So we know this is not a supernova. So we're not confused by supernovae. So this is sort of the detection of the earliest black holes in the universe. So I think I should stop here and open up the floor for questions, if I may. if that's appropriate. Yeah. Thank you very much to all of you for listening.
In your simulation there, you saw, of course, black hole is mainly formed by gravitational interaction, and you saw electromagnetic radiation, so you must have electromagnetic interaction. What role do the other two play, like the strong and weak interaction?
Sorry, what strong interactions?
Strong interaction, like in nuclear.
Yeah. So it turns out that in most sort of physical processes in the universe, gravity always wins. Gravity is really, on the scales that we're talking about, gravity is the strongest force, and it is the longest range force that we have in the universe. And as I said, I alluded to these phenomena couple very, very disparate scales. Yes. So the strong interaction per se is not at all relevant to the formation of black holes.
No, another question related to this is, for example, first pentosecond after the Big Bang, is the density higher than a black hole or lower?
That's a very nice question. It's not.
It's not?
No.
I see.
No.
Okay, so it's real singularity.
It's a real singularity. Absolutely. Yeah. Excellent question. Yeah.
How long ago are these very distant?
So this is when the universe was
the way little black holes.
1 billion, 1 gigayear, so 1 billion years after the Big Bang. So we define time as t equals 0 at the Big Bang, and we count from then on. So the universe's clock today is clocking at 13.7 gigayears or billion years. 13.7 billion is the age of the universe. So these guys formed in the first billion years after the Big Bang.
You always refer to a rotating disk.
Yeah.
Are you implying that it's always in 2 dimensions? And is there a mathematical reason why it's 2 dimensions?
No, it's always 3 dimensions. It's always 3 dimensions. It's just that the scale height of the disk is very small compared to the other 2 dimensions.
Is there a mathematical reason why?
Yes, so that's an excellent question. There's a very strong mathematical reason why a disk is what forms and it's not a sphere. And the reason for that is there's a lot of angular momentum or spin in the gas, and the way to actually be in equilibrium, the sort of lowest energy state for gas to be in an equilibrium with a singularity, with a very massive gravitating object in the center, is this configuration of an accretion disk. But then the challenge of the accretion disk is that because it has a lot of angular momentum, before the gas actually falls in splat onto the black hole, you have to lose angular momentum. That's why you have to grind down and you slowly come in. And so mass moves in, angular momentum moves out, and that's how you actually approach and fall on the event horizon.
And is there a theorem that states conditions such that a galaxy must have a black hole in the center?
There are no theorems, but what we do have is that we know the set of physical conditions that would produce a black hole. And what we find is that the majority of sites, there are a majority of sites in the universe where that could form. But your question, so one other thing that we find in these models, as I sort of alluded to, right, structure in our universe forms hierarchically. You form very little objects first, then they collide and they merge, and they form more massive objects. So that's how things assemble. So they assemble in a bottom-up scenario in the universe, right? And so in order for every galaxy in our neighborhood today to have a black hole in the center, it doesn't have to be born. The initials, each galaxy, because remember, Milky Way actually consists, assembled, we think, roughly with 25 collisions of equal mass or mass, unequal mass ratio 1:10 collisions over 13 billion years. That's how Milky Way has assembled, most likely. We have probability distribution, so this is the most probable way. And what we find of these pieces that came together, not every one of them needed to have its own black hole. So in order to produce what we see today, it's sufficient for every site in the early universe that could produce a black hole. If even 1/5 of them do the job, we're done. So it doesn't have to be very efficient. So black hole formation, seed formation in the very early universe does not have to be a super efficient process. The reason for that is that even if you seed in 1 in 5 by 13.7 billion years, because things form by merging, everyone ends up having one in the center.
You mentioned earlier you're going to tell us what happened when we fall into a black hole. Is that going to be falling through in the wormhole and merge in the second universe?
Yeah.
Or is it just speculation?
Well, I think the wormhole is a total speculation. And the second universe, I'll come to that in a minute. So what happens if I fall into a black hole is I will be spaghettified. Everybody will be, not just me, but everyone will be spaghettified. So you will be stretched out, and your third dimension, so if you really want to diet, this is pretty good thing to do, except there's no escape, right? So you would be pulled out, and your third dimension would become negligible compared to the other two. And you would whine, but then no one can hear you scream as you're falling into the black hole. Because remember, not even light can escape. Speed of light signals cannot come out of the event horizon, right? Forget about sound. So, and the interesting thing is, remember, this is the thing with infinities. So this is the mind-boggling concept about infinities, right? Because the potential, the sort of pinch in space-time is infinite. It'll take you an infinite amount of time to fall in. The reason it takes you an infinite amount of time, I'm just going to leave you all these crazy things to think about black holes, is that it takes you an infinite amount of time because once you enter the event horizon, your clock stops. So the interval between, a second, right? The interval that corresponds to a second, that actually approaches infinity once you fall into a black hole. So time stops once you go into a black hole. And the question of where does that go in? So I should come clean here. So there's a real speculative set of ideas, and I notice I'm going to say I believe. We can't know ever, but it's about belief and faith. So I actually believe that there are many, many other universes out there. Okay, so I believe in the multiverse, and so yes, we could tunnel and we could go somewhere. But the idea that the wormhole actually connects to another, that's highly speculative. We can never test it. But, I think it's kind of fun. But that's about it.
My question is about the empty donut. And you talked about when the inside gas, the gas around the mini black hole has exhausted.
Mm-hmm.
You said that it's going to take longer time
than the age of the universe at that time to refill that gap. Yeah.
So the age of the universe at the time of the formation?
No, at the time of this event. So when the merger happens, remember the universe has this clock that's ticking along. So these galaxies, these two galaxies that have merged, could have merged when, as I told you, this happens all the time. So this could have happened when the universe was, say, 12 billion years old. So what that means is the amount of time that it's going to take for gas to fill that cavity is longer than 12 billion years old.
So are there any observations recorded, events that occurred regarding how these black holes could have exhausted gas?
Yes. So we know, for example, so what we know is we see a lot of black holes in nearby galaxies, like our own galaxy, where there's no gas. There's stars, but there's no gas. So how did that happen, right? So we think that happened. So the storyline now is that the Milky Way, right, our galaxy had a merger, a very violent merger, not so long ago. So the gas was cleared out from that donut, and now all the gas that is around in the center here, around the innermost the merged black hole has been exhausted. And so what you're left with, what you're seeing when we now see the center of the Milky Way, is the location of the black hole, the evacuated gas donut, no gas donut, and a few stars that are swimming around.
So what happened to these fasting black holes?
They're just sitting there. They exert their gravity. They're sitting there. They exert gravity because they're pulling these stars that are rotating around them. That's all they're doing. And the thing is, the region of influence of a black hole depends on its mass. How far out their gravity is important. So remember, we are quite far away from the center of our galaxy. So we are about 10 to the 30 centimeters or so away from the center, 10 to the power 30, so 8 kiloparsecs away, right? And at the distance of the sun, or at this distance of the solar system, the black hole at the center of our galaxy does not matter at all. It's too wimpy to exert any gravity. And the only gravitationally dominant object for us is the sun. Exactly. So, the black hole at the center of the galaxy makes no difference. However, it makes all the difference for whatever gas lands right in there or whatever stars are right in there. Yeah.
So I was wondering, if we consider antimatter, could black holes, do you think that there are also black holes of antimatter, and how would that correspond to black holes, and what kind of interaction would they?
That's an excellent question. So it turns out there's another very interesting theorem which has a very peculiar name, and it's called a no-hair theorem. What that really means is that once the material crosses the event horizon, we have no idea of what it was. So you see a black hole, right? So we see the black hole at the center of the Milky Way. I can't tell you what it's made of. I mean, all my unmatched socks in my laundry could be in there, right? I mean, once any matter or antimatter, what have you, crosses the event horizon, you know nothing about it except the mass. So antimatter does have mass. So in fact, it's quite possible. There are some people have suggested that one of the peculiar things about our universe is that we started out probably with a slight asymmetry in matter and antimatter. And that slight asymmetry, so we have a little more matter rather than antimatter, and that has ratcheted down exponentially, and basically we now live in a region of the universe that's entirely dominated by matter. There's no antimatter at all. And possibly one speculation, which is still kind of wild speculation, is that perhaps all the antimatter, the deficient antimatter, is locked up in black holes. Now that would be quite a nice solution to the problem. Is what really made it all segregate and clump into little black holes? We don't actually know at all what physics that could be, but that's a great question.
And what about if there would be antimatter black holes? Would that mean that
we can never tell the difference? They wouldn't exert a different kind of gravity on the stars around them, nothing. There's no difference.
But if they would meet a black hole?
Yes, if they would meet a black hole, they would jiggle space-time in a different way. But as I told you, we've not detected any jiggling of space-time yet. But that would be an interesting signature. That could be a prediction. Great question.
Actually, the question she answered is just the question I want to
ask too.
just
About antimatter.
So what I want to add is that since there's antimatter and there's dark
Matter and there's
dark energy, is there any
No connection, unfortunately. It would solve so many problems, right? There are all these unknowns, and somehow if they were all X, that would be great. But we don't think there's any connection between antimatter and dark matter. And dark energy is a completely different beast. So actually tomorrow, I think, giving a public lecture on dark matter. And I'll try to sort of give you give a better idea of what all we understand about dark matter. We understand quite a lot right now, although we don't know what particle it's made of.
Okay, I have another question. Is that so you said that there's
There's a spin in the galaxy, and
the black hole
is
actually
spinning.
Black hole spins, and that is independent of the spin of the galaxy. And sometimes they can line up, sometimes they can be anticorrelated.
So I want to ask where actually did the galaxy did the black hole get the
Its spin.
Yes, it's spin.
So the way we don't quite understand how black holes get their spin, but we know how galaxies get their spin. And that is, if you remember the first movie one of the early movies that I showed you of the gas flows, notice that gas is flowing along filaments, right, in this movie. And there are torques that spin the gas around and actually generate. You can't see it in this movie because I need to rotate it, give you different angles to see the twisting. But you can imagine this is like ropes joining, right? Sort of ropes that are flowing. So there are lots of twists, there's lots of torques. And those torques generate a spin in the galaxy that's going to form, or the gas that is going to either flow into to feed the black hole or to make stars. Remember I told you it's the same gas reservoir from which you make both the stars and feed the black hole in a galaxy.
Okay.
Sorry, I think we should actually stop. So I'll say thank you very much, but I know that the kitchen staff are anxious to bring something else in.
Yeah. Thank you, Professor Natarajan, for the very insightful talk. I'm sure you've left us all with very boggled minds, and we'll be thinking about this all night. And hopefully you've inspired some people here as well. So if you would mind staying on the stage for Professor Melise to present you with a souvenir on behalf of our college.
Oh gosh. Oh wow. Thank you. Thank you.
And a big round of applause.
Thank you very much.
Thank you.
Should I just unhook
I just
this?
wanted to congratulate Priya on having brought dancing into astronomy, proving that every subject finds a role for sex somewhere. Now we've got pairs of black holes.